This is section 16.8 on Stokes' theorem, a higher dimensional version of Green's theorem in the plane. Right, so we're on page 1134. There's a picture of Stokes' theorem. All right, so you have a curve in space, and this little stick figure indicating the positive direction. So even though you're in space, generally we're going in a counterclockwise direction, right? And we're going this way. And if you're going in a clockwise direction, that's considered negative orientation. Okay, and a unit normal vector is considered positive if it's pointing upward. Right, so you are integrating along a surface, or you can just look at the boundary curve. That's what Stokes' theorem says. You can put this on your cheat sheet. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C. So surface, positive, up, and bounded by a curve C. Positive is counterclockwise. Okay. And capital F is a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Then the integral along the curve of f dot dr, which is work, is equal to a double integral of curl f dot ds. And this is similar to Green's theorem in the plane, which was back in section 4. So you have a choice. You can either integrate along the curve or integrate along the surface, the curl of f dot ds. And I'll show you in the homework, but because of this theorem, sometimes it'll say use Stokes' theorem to find the integral of f dot dr. It means to do this side. And then it might say use Stokes' theorem to evaluate this. It means to do this side. And I'll show you that when we get to it. All right, so put that on your formula sheet. The text goes over a special case of the proof. It doesn't even do the entire proof, but just a certain part of it, so you can look at it or not, as the case may be on 1135. But the idea is that you have a choice of either working on the surface itself or just the boundary. Okay, so page 1139. 1. Again, look at the language, 2 through 6. Use Stokes' theorem to evaluate double integral of curl f dot ds. It means do the integral along the curve of f dot dr. Similarly, for 7 through 10, use Stokes' theorem to evaluate integral of f dot dr. It means do the double integral of the curl of f dot ds because it turns out to be easier that way. Okay. Show you the rest of the problems. Okay, they don't give you that many, and I don't give you that many because otherwise some of the problems can get really long. Okay, number 1, just mention quickly. A hemisphere H and a portion of a paraboloid are shown. Suppose F is a vector field on R3 whose components have continuous second partials. Explain why the double integral of curl f dot ds along the hemisphere is equal to double integral of curl f dot ds along the paraboloid. And the reason is because they have the same boundary curve. So the answer that I put is they have the same boundary curve. Okay. In other words, they're both equal to the integral along the boundary curve of f dot dr. They have the same boundary curve. In some sense, that kind of makes sense. If you imagine a hose, a garden hose that has the same shape here, and you're shooting water out of it, it doesn't really matter what this shape is. It can go up like that. It can go up 1,000,000 miles and out. The same amount of water is going to go through the same boundary hole, as it were. If you're shooting water that's coming through, the same amount will flow through, whether it looks like that or it looks like that. All right, so again, 2 through 6, use Stokes' theorem to evaluate this. It means actually do that part over there. Okay. So number 5, bold f of x, y, z is this. Okay, the boundary curve is the bottom, z equals -1. It says in the language that S consists of the top and 4 sides, but not the bottom of the cube with vertices ±1, ±1, ±1 oriented outward. Okay. So the boundary curve is the bottom, z equals -1. So we break it up into its component parts. Now z is -1. If I plug in -1, that's -xy, that stays xy, and that's -x² y. Okay, so C is C1 plus C2 plus C3 plus C4. 1 arrow, 2 arrows, 3 arrows, 4 arrows. Work them all out. C1, Y is -1. X goes from -1 to 1. So I plug in -1 right there, that gives me X. -1 there gives me -x. -1 there gives me x². And Y is equal to -1. Okay, so R, position factor, is x, y, z. Well, y is -1, z is -1. Okay, so dr is 1, 0, 0. So f dot dr is just going to be x. So integral along C1 is integral from -1 to 1 of x dx, x² over 2 from -1 to 1, 0. C2, x is 1, y goes from -1 to 1. So I plug in x equals 1, that's -y, y, and -y at x equals 1. So position vector r, x is 1, y is y, z is always -1. For these, y goes from -1 to 1. dr is 0, 1, 0. So f dot dr, integral from -1 to 1 of y di, same thing, you get 0. C3, y equals 1. And this is tricky. X goes from 1 to -1. Again, we're going backwards here. We're going specifically in this direction in order to go counterclockwise. So 1 to -1. So R is X, Y is 1, Z is always -1 for this problem. dr is 1, 0, 0. F is, let's see, we're told that y is 1. So if y is 1, that's -x, x, and -x². And f dot dr is -x. So integral from -1 to 1 of -x dx also comes out to be 0. And finally, C4, x is -1, y goes from 1 to -1. Again, has to be 1 to -1 because we're going in this direction. So I plug in x is -1, that gives me y, -y, and -y. R is, x is -1, z is -1, y is y. So dr is 0, 1, 0. So f dot dr is 1 times -y, -y. Integral from 1 to -1 of -y is again 0. So therefore, the integral along the curve is integral along C1 plus C2 plus C3 plus C4, but they're all 0. So that's all there is to that one. Okay, number 7, they ask you to go the other way. Okay. Use Stokes' theorem to evaluate the integral of f dot dr. It means find a double integral of curl f dot ds. Okay, so number 7, you have x plus y squared, y plus z squared, z plus x squared. And C is a triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. Looks like this. Okay, so the unit normal vector is going to be 1, 1, 1 over radical 3. All right, so curl F is ijk, partial with respect to x, y, z, x plus y squared, y plus z squared, z plus x squared. So I component is that minus that, which is nothing minus 2z. Then the opposite of 2x minus nothing. And the k component is nothing minus 2y. So -2z, -2x, negative 2y. So curl f dot n, so that's going to be factor out the negative 2 over radical 3. You get z plus x plus y, or x plus y plus z. So the integral is a double integral of curl f dot n ds. Take out the negative 2 over radical 3. And you're integrating from 0 to 1, 0 to 1 minus x plus y plus z ds. But x plus y plus z is 1. All right, so z equals 1 minus x minus y. Therefore, I can use the formula negative 2 over radical 3 square root of 1 plus negative 1 squared plus negative 1 squared dA, or negative 2 over radical 3 times radical 3 times a half. That's the area in the xy plane of this object, and that comes out to be negative 1. This was 1 plus z sub x squared plus z sub y squared. Okay. 9, f of x, y, z is this. C is z minus 1 minus x squared minus y squared in the first octant. So curl f, I, j, k, partial with respect to x, y, z. X, y, y, z, z, x. Okay, so I component is nothing minus y. J component is the opposite of z minus x. And the k component is nothing minus x. So there we go. Okay, z sub x is negative 2x, z sub y is negative 2y. Okay, r is going from 0 to 1, theta is going from 0 to pi over 2 because we're told that we are in the first octant. Okay, at z equals 0, the xy plane, you have x squared plus y squared equals 1 unit circle. All right, so double integral of curl f dot ds. This time I use the formula negative p z sub x minus q z sub y plus r dA. Okay, and I just mentioned that it's too long. So that's why I only show you a quick setup of that. Okay, 13, I changed the problem to only doing integral of f dot dr because the other one turns out to be too long. The original problem says verify that Stokes' theorem is true. That really means do both sides. Okay, it's too long to do both sides. Okay, so we'll only do the f dot dr part. All right, so the boundary is x squared plus y squared equals 4 squared or 16. Switch the polar coordinates. X is 4 cosine theta, y is 4 sine theta, and z is equal to 4. So f is negative y, negative 4 sine theta, x for cosine theta, negative 2. So r prime or dr, so the derivative of this is negative 4, sorry, dr. dr is the derivative of this, negative 4 sine theta, derivative of that is 4 cosine theta, derivative of that is 0. And then f dot dr, right? So that times that, 16 sine squared, plus that times that, 16 sine cosine squared. That times that is nothing, so that comes out to be 16. All right, so the integral of f dot dr is negative because it says downward. Negative the integral of 16 d theta from 0 to 2 pi. So multiply this, negative 32 pi. $15, again, we're only going to do the integral of f dot dr for simplicity. F is yzx along x squared plus y squared plus z squared equals 1. Y is greater than or equal to 0, so it's a hemisphere. Positive y-axis is actually negative because that's considered inward. Okay, so we want the opposite of the answer that we get. And the boundary curve is x squared plus z squared equals 1, y equals 0. Okay, so the boundary, r, x is 1 cosine theta, y is always 0, z is sine theta. So f is 0, is yzx, so 0, z sine x, and cosine theta, which is x. R prime is negative sine theta, nothing cosine theta. So f dot dr, that times that is nothing, that times that is nothing, that times that is cosine squared. So I want the opposite of the integral from 0 to 2 pi. Again, it's negative because it says in the direction of the positive y-axis, but for this picture, it's going inward. So inward is considered negative. So negative integral from 0 to 2 pi of cosine squared. Cosine squared is 1 plus cosine 2 theta over 2. Take out the half. Theta plus 1/2 sine of 2 theta. Plug in 0, you get 0. Plug in 2 pi, that's 0, but this is 2 pi, negative a half times 2 pi, negative pi. And 17, particle moves from the origin to 1, 0, 0, 1, 2, 1, 0, 2, 1, back to 0 under the influence of the force field F. Find the work done. Okay. So here's my picture. All right, so I analyze along C is L1 plus L2 plus L3 plus L4 along those 4 curves, C1, C2, C3, C4, equivalently. Okay, L1, going from 0, 0, 0 to 1, 0, 0 in a straight line. So X is T, Y is 0, Z is 0. So plugging in, F is 0, 0, 0. R prime is 1, 0, 0. F dot dr is 0. So that means when you integrate, you're integrating 0, so you end up with 0. L2, X is 1, going from 0, 0 to 2, 1. So parametrically, Y equals 2t, Z is t. So F, again, for this one, Z is 0, so that's 0. Y is 0, that's 0, that's 0. This is a little bit harder. So X is 1, that's a 1. Z squared is t squared. And 2xy is 2 times 1 times 2t, or 4t. And then 4y squared is 4 times 2t quantity squared, or 16t squared. All right, R prime is 0 to 1. F dot dr. So that times nothing plus 8t plus 16t squared. So that's what I'm integrating from 0 to 1. 8t plus 16t squared, 4t squared plus 16t cubed over 3, 28 over 3. L3, from here to here, okay, so you can use that formula where R of t is what? 1 minus t times this vector plus t times that vector. So here we are, 1 minus t r sub 0 plus t r sub 1. All right, so x is 1 minus t, y is 2, z is equal to 1 constantly. All right, so f is 1, 4 times 1 minus t, and 16 times 1, or 16. R prime is negative 1, 0, 0. And f dot dr is negative 1. So integral from 0 to 1 of negative 1, negative 1. And finally, L4, let's see, x is equal to 0. Y is 2 minus 2t, z is 1 minus t, just going from one point to the other, going from here to here, and applying this formula. So f is z squared. We saw where to go. So yeah, then 2xy, so x is 0, and then 4y squared, 4 times 2 minus 2t squared. And what's r prime? Nothing, negative 2 and negative 1. So f dot dr, that times nothing, that times nothing, that times negative 1. So negative 4 times 2 minus 2t squared. Factor out to negative 4. All right, so negative 4 2 minus 2t cubed over 3, then by the chain root times the -2. Plug in 0, you do not get 0. Actually, when you plug in 1, you get 0, right? Plug in 1 there, you get 0. Plug in 0, you get 2 cubed or 8 divided by -6. 2/3 times -8, -16 over 3 is the answer. Okay, so that's section 16.8.